Welcome back to another journey into the deep cosmos, specifically crafted for the curious minds watching dark sky dive today. Landing on a massive planet is difficult, but touching down on a small, spinning asteroid presents a unique set of challenges. Without enough gravity to hold you down, a simple touch can send a spacecraft bouncing uncontrollably back into the void. This is why we need a specialized solution. A machine designed not just to land, but to anchor itself permanently. We begin our manufacturing journey with the Harpoon legs system, the primary mechanism that ensures our vessel stays on the ground. Raw titanium is heated to extreme temperatures until it flows like liquid fire, ready to be cast into complex shapes. The molten alloy fills the high-precision molds, forming the skeletal structure that must withstand the harsh conditions of deep space. As the metal cools and hardens, we break away the ceramic shell to reveal the incredibly strong titanium leg frame. Robotic arms equipped with high-powered lasers trim the excess material, ensuring every millimeter of the leg meets our exact specifications. Quality control is paramount here, as even a microscopic fracture could lead to catastrophic failure during the crucial landing sequence. Hydraulic joints are installed to give the legs flexibility, allowing them to absorb the initial shock of impact without breaking. The tip of the harpoon is ground to a razor edge, capable of piercing through the frozen crust of asteroids. Inside the harpoon, we carefully install a small explosive charge that will drive the anchor deep into the rock instantly. This diagram illustrates the mechanism firing immediately upon contact, securing the spacecraft before any rebound force can push it away. We test the firing mechanism on reinforced concrete, observing how the cable pulls tight to simulate a successful planetary capture. The tether connecting the anchor is made from advanced polymers, designed to withstand tons of tension without snapping under pressure. A final protective coating is sprayed over the assembly to shield the metal from cosmic radiation and extreme thermal fluctuations. One leg is now complete, standing ready as a masterpiece of engineering, combining brute strength with sophisticated deployment technology. 4 of these legs are attached to the main chassis, giving the lander a stable and predatory stance, like a spider. Computer simulations verify the synchronized movement of all limbs, ensuring they can adapt to uneven terrain upon landing arrival. From this angle, we can see the harpoons primed and ready, the silent guardians that will determine the mission's success. We now move to the clean room for the second phase, creating the delicate cold gas thruster system for navigation. Using advanced metal additive manufacturing, lasers fuse layers of powder to create geometries impossible to achieve with traditional casting. These micron nozzles are printed with internal channels so complex that they can precisely control the flow of gas. Once printing is complete, we remove the excess powder to reveal a nozzle cluster that is a work of art. Under an electron microscope, the precision is undeniable, ensuring that the gas expands exactly as predicted by our physics models. Technicians install miniature solenoid valves, which will pulse rapidly to release tiny bursts of nitrogen gas for maneuvering. Micro-laser welding connects the supply lines, creating seamless joints that prevent even the smallest molecule of gas from leaking. The nitrogen fuel is stored in high-pressure tanks wrapped in carbon fiber, offering the best strength-to-weight ratio available today. We connect the tanks to the nozzle assembly and pressurize the system to verify that every seal is absolutely perfect. The entire thruster unit is placed inside a vacuum chamber to simulate the airless environment it will soon operate in. Upon activation, pure white plumes of nitrogen shoot out in straight lines, unaffected by atmospheric disturbance in the vacuum. High-speed cameras capture the expansion of the gas, confirming that our nozzle design provides the maximum possible thrust efficiency. We run a stabilization test where the system automatically pulses gas to keep a floating object perfectly still and balanced. Thermal imaging reveals the intense cold generated at the nozzle tip, a challenge our materials must withstand without becoming brittle. Satisfied with the performance data, our engineers sign off on the propulsion system, moving us closer to the final assembly. The thruster modules are integrated into the main chassis, nestled strategically between the landing legs for optimal center of gravity. The spacecraft is taking shape, evolving from a collection of parts into a cohesive machine ready for the void. We now enter the precision machining area for Phase 3, focusing on the microspine grippers, the hands of our explorer. Thousands of tiny hooks are cut from high-strength steel using electrical discharge machining to achieve razor-sharp edges and durability. Each individual hook is shaped like a microscopic claw, designed to catch on the tiniest imperfections of a rock surface. These hooks are assembled into a flexible matrix that mimics the biological gripping mechanism found on the feet of geckos. The design allows each spine to move independently, finding its own grip point on the rough, uneven surface of the asteroid. In our testing facility, we press the gripper against jagged rocks and apply force to verify it won't slip off. Macro cameras reveal how the steel spines dig into the microscopic pores of the stone, creating a nearly unbreakable bond. Even on surfaces covered in slippery ice, the sheer number of spines ensures that enough of them find a hold. Tiny damping springs are installed behind each spine to distribute the load evenly, preventing any single hook from snapping. The completed gripper pad looks like a futuristic chainmail, a mesh of steel ready to conquer the smooth and the rough. We attach these gripping pads to the soles of the harpoon legs, adding a secondary layer of security to the landing. Now the lander feet possess a dual-action system, deep penetration from the harpoons and surface friction from the microspines. Endurance testing involves engaging and disengaging the grippers thousands of times to ensure the springs don't lose their elasticity. Special space-grade dry lubricants are applied to the moving parts, preventing them from freezing solid in the cold of space. To demonstrate versatility, we show the gripper lifting a smooth metal sphere, proving it can handle more than just rock. Legs, thrusters, and grippers are now united. The vehicle is robust, but it still lacks the tool for its scientific mission. We enter the final manufacturing phase in the geology lab to build the cryogenic drill, the heart of the scientific mission. Industrial diamonds are selected for their hardness and are carefully faceted to form the cutting teeth of the drill bit. These diamonds are embedded into a tungsten alloy matrix, creating a drill head capable of grinding through the hardest basalts. The drill features a hollow core design, allowing it to capture a pristine cylinder of rock and ice as it descends. Spiral flutes are machined into the shaft to transport debris upwards, preventing the drill from getting stuck deep in the hole. We couple the bit with a compact high-torque motor, designed to deliver immense rotational force without overheating in a vacuum. Testing begins on a block of deep-frozen permafrost, simulating the concrete-like hardness of ice found on distant celestial bodies. A borescope camera reveals the smooth progress of the drill, cutting cleanly without melting the ice and contaminating the sample. Once the depth is reached, an internal shutter mechanism snaps shut, securing the precious core sample safely inside the tube. We manufacture hermetically sealed containers equipped with double O-rings to ensure no volatile gases escape during the return trip. An automated transfer system moves the core from the drill to the storage canister and seals it tight instantly. Helium leak detectors verify the integrity of the seals, confirming that the sample will remain pristine for millions of miles. The entire drilling rig is mounted to the underbelly of the spacecraft, directly in the center to maintain stability. We test the deployment rails, watching the heavy drill assembly slide down smoothly to its working position and retract back. The assembly is now complete. Our engineers stand back to admire the culmination of thousands of hours of design and labor. A final visual inspection takes us around the craft, seeing how the legs, thrusters, and drill integrate into one unit. Before it can fly, it must survive the launch. We strap it to a vibration table to simulate rocket liftoff. The violent shaking tests every bolt and weld, proving that our manufacturing quality can withstand the journey to orbit. Past all tests, the lander is carefully encapsulated inside the rocket's payload fairing, ready to leave Earth behind forever. Engines ignite, and the rocket climbs into the sky, carrying our mechanical explorer away from the safety of our home planet. High above the atmosphere, the fairing falls away, and our spacecraft begins its long, silent cruise through the darkness. Leaving the moon behind, it ventures into deep space, navigating by the stars towards its tiny, distant target. Months of travel pass in silence until finally, the rugged shape of the target asteroid appears on the navigation sensors. The asteroid is a chaotic world of rubble, spinning rapidly, making the approach vector extremely difficult to calculate and execute. The cold gas thrusters we built spring to life, firing short, precise bursts to match the rotation of the rock. Onboard cameras show the surface rushing up to meet us. The computer autonomously selects the flattest possible landing site. The titanium legs extend fully, bracing for impact. This is the moment where engineering meets the chaotic reality of space. Contact. Sensors detect the touch, and milliseconds later the explosive harpoons fire, driving anchors deep into the frozen soil. The anchors bite hard. The cables pull tight, counteracting the bounce and pulling the spacecraft down firmly against the surface. Simultaneously, the microspine grippers engage, thousands of steel claws locking onto the uneven texture of the asteroid's skin. The ship is secure. It rides the spinning asteroid like a barnacle on a whale, stable and ready for science. With a stable platform established, the cryogenic drill lowers. The diamond tip begins to spin, hungry for the secrets below. It cuts into the ancient ice. Dust rises but floats lazily in the microgravity, creating a cloud around the worksite. We drill down 2 meters, passing through layers of dust and ice that have remained untouched for billions of years. The drill retracts, bringing with it a cylinder of material that could hold the clues to the origin of water. The sample is transferred to the hermetic container. The seals lock tight, preserving the alien atmosphere inside for analysis back home. Mission accomplished. It is time to leave. Explosive bolts cut the harpoon cables, leaving the anchors behind as permanent markers. The grippers release their hold. The legs compress one last time, preparing to push the vessel away from the rock. Thrusters fire in unison with the jump. The spacecraft ascends, leaving the desolate, spinning world of the asteroid behind. As the asteroid shrinks in the distance, we reflect on the incredible engineering that made this brief touch-and-go possible. The return journey begins. The precious cargo is safe, and the ship navigates by the beacon of the pale blue dot. Seeing the manufacturing process alongside the mission footage reminds us that every minute spent in the workshop ensures success in space. From the molten titanium fires to the icy grip of the harpoon, the legs performed exactly as they were designed to. The microscopic precision of the printed nozzles allowed for delicate ballet-like maneuvers in the unforgiving vacuum of the void. The Gecko-inspired grippers proved that sometimes nature has the best engineering solutions, even for machines built of cold steel. And the diamond drill, the tip of the spear, successfully harvested the building blocks of the solar system for us. Back on Earth, the control room erupts in cheers. It is a victory not just for science, but for manufacturing excellence. Fast forward to the end of the saga. The sample capsule streaks through the atmosphere and splashes down safely in the ocean. Recovery teams hoist the scorched capsule onto the deck. The journey is over, but the scientific discovery is just beginning. In a sterile lab, scientists finally open the container we built. The dust inside is older than the Earth itself. Looking at these grains under a microscope, we are looking back in time, understanding how our solar system came to be. This technology paves the way for the future, not just for science, but for mining precious resources from these celestial rocks. Imagine a fleet of these anchor ships built on assembly lines, heading out to harvest platinum and water from the asteroid belt. The gripping technology could allow robots to build structures, anchoring habitats to spinning rocks to expand human presence outward. But it all starts with this one prototype. It stands now in a museum, a testament to the ingenuity of its creators. The scratches on its legs tell the story of its struggle against the void, a battle won through precision engineering. The engineers who built it look on with pride, knowing their hands shaped metal that touched the fabric of deep space. Let us take one last look at the symphony of sparks, lasers, and metal that brought this incredible machine to life. The fire of the foundry, the precision of the laser, and the cold logic of the code all played their part. Every component, from the smallest screw to the largest tank, was essential. There is no room for error in the void. We push the boundaries of manufacturing not just to explore, but to understand our own place in this vast, beautiful universe. Dark Sky Dive is committed to bringing you these stories of technological marvels, bridging the gap between imagination and reality. If you enjoyed this deep dive into spacecraft manufacturing, please consider subscribing to support our channel for more detailed content. Check out our other videos where we explore the engineering behind deep-sea submersibles and hypersonic aircraft engines. Behind every great machine are the human beings who dream it up. We salute the engineers and machinists of the world. Innovation is a messy process. It takes failure, revision, and persistence to create something that can survive the anchor of the void. As we look to the stars, we remember that the tools we build are the stepping stones to our future among them. The anchor is cast, the sample is secured, and the ship drifts on. A silent voyager in the endless, dark ocean. Next time you see a shooting star, imagine it might be a traveler returning home with secrets from the dawn of time. Thank you for watching this episode of Dark Sky Dive. We hope you found the engineering behind the mission fascinating. Special thanks to our research team and visual artists who worked tirelessly to visualize this complex mechanical journey for you. We draw inspiration from real-world space agencies and their incredible missions to asteroids like Bennu and Ryugu in recent years. Stay curious, stay inspired, and keep looking up. This is Dark Sky Dive, signing off until our next adventure. Goodbye for now. See you in the next video.